The next talk is Garbage Collection in V8 by John Stephenson and Richard Abou Chaaya from Trenchant.
Hi everyone, thank you for joining. Today we're going to talk about garbage collection in V8. We have two main bugs that we want to discuss that will constitute a full remote code execution exploit against Chrome. But to get there, we need to learn about some garbage collection theory, focusing on the pointer finding problem. Then we'll see why recent changes in this area led to the introduction of a new garbage collector in V8 called MinerMS. We'll talk about an issue that was fixed last year and that was considered non-exploitable at the time, but we'll see how it becomes exploitable under the new MinerMS garbage collector. After that, we'll talk about the Heap sandbox and how it interacts with garbage collection, and discuss a GC-related Heap sandbox escape. So the goal of garbage collection is to determine which objects are still alive, that is to say they can still be used and interacted with by the runtime, and free the rest. This is usually done by first establishing a set of roots, which are objects that are known to be alive by virtue of being referenced from a live stack frame or a register, for example, and then following pointers from these objects, marking the objects encountered along the way. At the end of this process, all the objects that were not marked are considered unreachable and can be freed. Another important concept is the generational hypothesis. It's really an observation that most objects die young, and that if an object survives for a couple of garbage collection cycles, it's likely to survive for more. So to take advantage of this, allocators usually divide the heap in two spaces, one for young objects and one for old objects that are garbage collected separately. And the idea is that the young space will be garbage collected much less often than the old space. The way it works is that initially, objects are allocated in the young generation, and if they survive for a couple of garbage collection cycles, they're promoted to the old generation. To perform garbage collection, we need to find pointers to objects. This is useful to build the initial set of roots and perform marking, but also to update these pointers if an object gets moved, which can happen, for example, due to compaction. That's when objects that are live get moved close together to reduce fragmentation in the heap. In V8, on the heap, this is done by having every object describe its own layout. So there are type-specific visitors implemented for every type that inform the GC about where pointers may be found in any given object. On the stack, however, since the layout of C++ stack frames is not well defined, it's not easy to know where pointers may reside. So to deal with this, we need to use one of two strategies, precise route tracking or conservative stack scanning. And an ongoing project in V8 is to move from precise route tracking to conservative stack scanning. So we will discuss both options and see why they want to switch. So currently in the V8 codebase, there's this special class called handle that's used to represent references to the JS heap. Declaring a handle informs the GC that the object is alive and it should be used as a root because it's referenced from a C++ local variable. If we were to use a direct pointer instead of a handle, the GC wouldn't know about the object and could potentially free it, or it could move it without updating the pointer, leading to a dangling reference. The advantage of having a separate class to represent references is that through the constructors and destructors, we can easily get callbacks when a reference is created or destroyed. And having these callbacks whenever references are created or when they go out of scope makes it easy to always track the set of live references at any given point. And since we know with this approach, we know precisely the set of roots at any point in the execution, This approach is called precise route tracking. Sorry. However, since creating and destroying handles happen very often, having an additional callback every time comes at a significant runtime cost. Internally, the handles just add a level of indirection. So the handle points to an entry inside the handle block, which in turn contains the pointer to the actual object on the JS heap. So these handle blocks are updated whenever handles are created or destroyed, so they naturally track the set of routes. Another advantage of this scheme is that if an object gets moved, only the entry in the handle block needs to be updated. The handle, which is the actual C++ local variable, doesn't need to be changed, which might be tricky for reasons that we'll discuss later. Here's an example of using handles. You must first declare a handle scope, and then by default, all the handles are associated with the most recently declared handle scope. When that object goes out of scope, all its associated handles are invalidated. So in this example, there's actually a bug, because we are returning a handle that's associated with a handle scope that was declared in the same function. So that handle scope is destroyed at the end of the function, and the returned handle is not valid in the context of the caller. To fix this, a developer would need to manually escape the handle because it outlives the handle scope in which it was initially declared. What I want to point out with this is that with precise route tracking, a lot of the burden of route management is put on the developers. Additionally, if a developer knows that garbage collection cannot occur in some part of the code, they can decide to use direct pointers instead of handle to get better performance, to avoid the additional dereference and avoid getting those extra callbacks. However, we end up in a situation where using a direct pointer when GC can occur can lead to a use after free or a dangling pointer. And conversely, using a handle when GC cannot occur leads to bad performance. They have some toolings in the V8 project, namely this GC mole tool, that tries to statically look for handle misuse. So it tries to look for patterns such as the one described in the README, where a reference is declared, but without a handle, for example. Then garbage collection is triggered, and the reference is later used. The problem is that the garbage collection might invalidate the reference in between the declaration and the use. But this tool is not perfect. Here's an example of some code that's currently in the code base. It's a function that's responsible for calculating source positions in inline functions. As you can see, they declare a reference to some de-optimization data using tagged. And tagged is not a handle, it's just like a direct pointer. Then the source position info constructor is invoked. And this constructor can trigger garbage collection because it allocates. Here's the call stack that goes from the source position info constructor to a fixed array allocation on the heap. And any allocation might trigger GC. And after that, the deopt data is dereferenced. So the problem is that if the source position info constructor triggered garbage collection, the GC might have moved the deop data somewhere else. And since the reference was not using a handle but just a direct pointer, the pointer doesn't get updated to reflect the new location, and we end up with a dangling pointer access. In our estimation, this particular example is not exploitable, but if you think otherwise, then please feel free to reach out. So now that we understand how route tracking currently works in V8, and we know about the annoying trade-off that currently exists between performance and security, I will hand it over to John to talk about recent developments in the area.
So we've seen how the use of handles to track garbage collection routes has these undesirable security properties. And additionally, using handles to track routes can cause a performance cost that's associated with allocating an object for every such reference. So in order to address this, there is ongoing work in V8 to move away from handles and to use direct pointers in C++ stack frames instead. And recall that here, garbage collection is occurring in an environment with two language runtimes. And for JavaScript, the JavaScript runtime, the stack frame layout can be known exactly, and so the location of pointers is known. But without handles in a C++ stack frame, every value on the stack has to be treated as a potential pointer and therefore a root. And this approach is referred to as conservative stack scanning. The idea that we have to assume anything on the stack can be a pointer might seem a bit strange, so we'll walk through an example. In the normal case, as we iterate a C++ stack frame, we read values and decide whether they might point to an allocation. And this is done by checking that they point within a range describing possible addresses. If some value happens to point into the heap, this counts as an object being pointed to being reachable. However, if every value is treated as a pointer, what happens if we encounter some pathological value that looks like a pointer but isn't? If a number like this is found that happens to look like a pointer to somewhere in the heap, it must also be treated as a root, and the corresponding object won't be freed. So in our diagram, we have a number that points to the same location as a real address, but in the general case, even if a number happens to point to some object that would otherwise be freed, it'll count as being marked. And this isn't too bad, it just means that the set of roots is over-approximated. But this situation does impose a concrete restriction on a garbage collection algorithm. And we'll see shortly that some garbage collection approaches might move objects, and this is incompatible with conservative stack scanning, because if we move an object, we have to also update all of the references to that object to reflect its new location. But if some referring value was not a pointer, but just, for example, a misclassified integer, we'd end up modifying it and thus corrupting its value. So conservative stack scanning can only be used if the GC algorithm offers a mechanism for pinning objects in place. And so just to recap, we have two approaches that can be used for finding pointers in these C++ stack frames. The precise approach, where the exact set of roots is known, meaning that we may move objects in our GC algorithm. And in this approach, the developer is responsible for understanding whether garbage collection can occur in a given scope, and therefore whether references should be wrapped in handles, which is fundamentally error-prone. And the conservative approach is instead transparent to developers, and the mutator throughput is higher because we don't need to allocate a handle per reference. However, there is a limitation that the GC algorithm, in that case, can't move objects because misclassified non-pointer values might then also be updated and corrupted. Currently, V8 uses a collector called the scavenger to perform young generation garbage collection. Let's walk through how it works at a high level. The scavenger partitions the heap into two spaces, labeled the from and the to space. New allocations are serviced by the from space. On collection, marked objects are moved to the to space. Any objects that are not marked are simply left behind. And the advantage that moving objects like this provides is that all live objects will now be compactly allocated in the to space. Once all the live objects are moved, the from space is empty. Then the labels are swapped, so the from space becomes the to space and vice versa. And then new allocations can now start in the new from space, and the process repeats. And this approach is nice because it has really good compaction properties. Memory fragmentation generally leads to inefficient use of memory, so this avoids wasting small bits of memory in between objects. However, as we mentioned earlier, moving objects in this way is incompatible with the conservative root finding approach. And this has motivated work in the GC to develop an approach that does not move objects and is therefore compatible with conservative stack scanning. An approach taken by the V8 team was to implement a new mark sweep-based strategy for the young generation called minor mark sweep. As a last bit of theory before we talk about some bugs, let's have a high-level look at how minor mark sweep works. Here. And as the name suggests, at a very high level, minor mark sweep marks live objects, and then sweeps the heap, iterating objects and freeing regions that are not marked. Earlier in our discussion of the scavenger, we mentioned marking, but we didn't give much detail about what this actually looks like, so let's have a look at what it looks like in minor MS. So as always, we start with some set of allocated objects. In this case, minor MS will use a bitmap to track live memory in the heap. The marking algorithm starts at the set of roots, traverses the object graph to find live objects, and then for each live object in a region, a bit in the marking bitmap is set to indicate that there is a live object at that place in memory. Sweeping amounts to a traversal of the heap, and using the bitmap, it's possible to iterate or advance to the beginning of each live object. And specifically, for each live object in the heap, a bit in the bitmap will be set to indicate the address of the beginning of this object. And then dead objects can return their allocations, and the free space between objects is coalesced and collected into a free list, which is used in servicing subsequent allocations. The gaps between the objects that remain alive are also filled with the special free space internal object that can be traversed and accounted for by subsequent marking phases in subsequent collection rounds. One interesting aspect of MinerMS's design is the mechanism by which it promotes objects from young to old space. Recall that if an object survives some number of garbage collection rounds, it should probably be promoted into a space that is collected less often. And MinerMS actually promotes objects with page granularity as a way to overcome the inability to actually move objects. So if an object in a given space survives some number of collections, the entire page housing that object will be promoted. And the page will also be promoted if less than some specific threshold of memory was allocated from the page in the last round. And they use this as a heuristic to determine whether a page has a high degree of fragmentation. So a final recap of the motivation behind the development of MinerMS. There are good reasons to move from an indirect handle approach to a direct pointer approach to GC root tracking. This requires conservative stack scanning to find pointers in C++ stack frames. Under conservative stack scanning, objects referenced from the stack cannot be moved. The current design of the scavenger always moves live objects, and so one approach to solve this was to implement a new young generation collector that does not move its live objects. So what is the development status of MinerMS? It has been under development for quite some time, with the first commits relating to young generation mark compaction landing the better part of a decade ago. The feature is now fully supported in Chrome and is no longer experimental. However, it is not enabled by default. Last year, Chrome performed some field trial testing for some months, meaning that the feature was randomly activated for some percentage of Chrome installations. And the results appear to be that MinerMS represents a considerable memory consumption regression due to having higher heap fragmentation, which has blocked its full deployment. It is still actively supported and actively developed, but the V8 team is also developing a strategy for achieving object pinning in the scavenger to try and achieve their goal of a non-moving young generation collector. So not clear if it will be fully used in the future, but it is still under active development and is actively maintained. I'll now pass back over to Richard to discuss an issue that became exploitable under MinerMS.
Thank you. So we're going to talk about this issue that was fixed last year. And it was considered non-exploitable, but we'll see how it becomes exploitable under the new, under the new MinerMS garbage collector. It's an issue related to left trimming, which is an optimization that takes place when shifting arrays. In JavaScript, arrays have a shift method which moves over all the elements by one step to the left, and the first element is removed and returned. On the JavaScript heap, the element array looks like this. It's just a map, a length, and then the elements. So conceptually, shift just copies over all the elements by one slot to the left. A naive implementation of this would be of linear time complexity. So the idea of left trimming is that instead of copying all the elements by one slot to the left, we can just copy the array header by one slot to the right and update the pointer to point one step forward. So we end up with the same view of the array, but this can now be done in constant time. However, the problem is that this leaves a hole where the array used to start, and this hole is overwritten with a filler object. The reason we need these filler objects is that parts of the code, in particular the sweeper, traverse the heap by jumping from one object to the next. And they assume that the end of an object is always immediately followed by the start of another valid object. So since left trimming leaves a hole where the array originally started, it would break the traversal. So that's why we need to insert these filler objects. In the image here, you can imagine that the third object is an array that gets left trimmed a few times. So we need to insert as many filler objects for the traversal to keep working. So let's talk about the sweeper in a bit more detail, because it will be used in the exploit. It's the part of the code that actually frees objects. So it traverses the heap, it jumps from object to object, and frees the space in between marked objects. The free space itself has to be a valid object, because in order for future traversals to keep working. So in this case, it's a simple object that just has a map, a size, and a next pointer field, such that the free spaces can be organized in linked lists. So now we can understand the root cause of the issue. What happens is that a pointer to an element array gets spilled on the stack. Then the array is left trimmed. And so now the spill slot points to a filler object instead of pointing to the array. Now their conclusion was that this is not a problem as long as the array is no longer used after that point. But what can happen is that the GC might visit the stack frame and the spill slot and end up marking the filler object. Now, here's the initial proof of concept that we got through fuzzing. It just creates an array, calls .shift a few times, which causes register spilling, which causes left trimming, excuse me, and finally triggers some register spilling. If you run this in a vulnerable version, you will get an assertion failure complaining about the free space being in the marking work list. Now, to understand why that's dangerous, we need to learn more about filler objects. And with regard to GC, they have a special property in that they get freed even when they're marked. The reason is that filler objects appear when an object gets shrunk. So if the initial object was marked, then the filler objects will also be marked. But they really represent placeholders for memory that was wasted for some reason, and that we would like to reclaim on the next GC. So that's why they have this special property where the GC will free them even when they're marked. So with that, I will now walk through the exploit strategy that we used. Initially, we have a pointer on the stack that's pointing to an element array. The element array gets left trimmed a few times. And so now the pointer points to a bunch of filler objects. The filler objects are marked because they're referenced from the stack, but because they have this special property that we just talked about, they still get freed. And so we're now able to reclaim the memory that's pointed to by the stack. And our idea to exploit this is to place there a JS array and some data that will get interpreted by the GC to be a fake object that overlaps the JS array right up until its length field. The advantage of this is that once the sweeper comes along, it will jump from object to object. In particular, it will jump over the fake object because the fake object is marked because it's pointed to by the stack. And then the sweeper will consider that everything from the end of the fake object to the start of the next marked object is free. And so it overwrites it with a free space. And in particular, the free space map overwrites the length field of the JS array. Now, the difficulty is that we need to craft this fake object to have a very specific size, because we need to overlap the JS array and end exactly at the length field. So to do that, we decided to spray many fixed double arrays of decreasing size. Fixed double arrays are convenient because it's just a map and a length, so we can easily control the length of the fake objects. And having this pattern of decreasing sizes means that regardless of the exact alignment of the spray, regardless of where the spill slot ends up pointing in the spray, the object there will always be interpreted to have the right size and end at the target location. Here's the core of the exploit. We prepared a spray of fake fixed array of decreasing sizes. Then we trigger the bug by left trimming and causing register spilling. we reclaim the memory of the filler object with the target arrays whose size we want to corrupt and the spray of fixed arrays of decreasing sizes. And finally, we check if we were successful in corrupting the lengths of one of the arrays. Here's what the output looks like. The length should always be 1, up until at some point, the sweeper will have overwritten the lengths of one of the arrays with a free space map. Now, having an array with a corrupted length is an exploitable condition in V8. But in the interest of time, I won't detail how to go from this to arbitrary read-write over the JavaScript heap. But there are many resources online if you want to learn about it. So now that we have our initial exploit, I will hand it over to John to talk about the heap sandbox.
So in keeping with the theme of this talk, we also wanted to talk about the V8 heap sandbox in the context of garbage collection. If you were here last year, you may recall Samuel's talk on the V8 heap sandbox. We won't rehash the implementation in as much detail, but I want to cover its objective at a high level. The goal is to constrain memory corruption in the V8 heap to the V8 heap, such that any further corruption should not be able to facilitate arbitrary reading and writing or code execution. For example, using a heap out-of-bounds primitive such as the one we just demonstrated, an attacker may formally have been able to reach objects that trivially provide arbitrary read and write, and then, for instance, the ability to write code directly into read-write executable regions of memory allocated by a WASM instance, for instance. Now, such a primitive should be constrained to the heap sandbox. An attacker should not be able to leverage it to, as such. One of the key aspects of its implementation is the use of various external spaces to house objects that could be prone to corruption in this way. As an example, we'll take a look at how the sandbox brokers access to DOM API objects. We'll use a DOM point as an example of an object that holds data that lives in a sandbox external space, and in this case, the blink heap. So when accessing an object that refers to an allocation in an external space, such as the blink heap, we can't just hold a raw pointer in the V8 object, as this would allow for trivial corruption by, for instance, altering that reference to point anywhere. And therefore, access to these external objects must be safely brokered through pointer tables. And here's what that might look like. So within the sandbox, the V8 wrapper object holds an index into a table of full width pointers, which can then, in turn, point into the blink heap. The table is outside of the sandbox, so as the attacker, the best we can do is to point the index to a different table entry. So if we start with a layout like this, with two V8 wrappers of different types referencing their corresponding blink heap objects, we can point the embedder field of one to the table entry of another. And this used to be exploitable during the intermediate stages of the sandbox's development. The GitHub security blog has a nice post detailing how it was possible to achieve a sandbox escape by confusing DOM-rect and DOM-typed array in this way. The way this works is that calling methods on DOM API objects will be blindly invoked on the corresponding blink heap object, as resolved by the pointer table. So taking DOM-rect object, which has full width inlined data on the blink heap, and then calling getters and setters allows us to potentially manipulate full width pointers in the body of the confused object. The way this was solved in V8 was to tag each table entry by setting some bits in each address. So access to these table entries through, for instance, method calls now must use the correct tag to ensure that the table entry referenced points to an object of the correct type. And with a high enough tag granularity, the system becomes robust to this sort of substitution attack. Here's an example of from the x64 macro assembler. And the notable thing is that on any access to some trusted field, the trusted pointer table entry will be resolved by index, and if the table entry does not point to the correct type, then this untagging will result in some high bits being set in the resolved address, causing an invalid access. So here is a snippet of code that shows how pointer tagging was formally implemented. So during the construction of pointer table entries in the C++ heap pointer table, we see the raw pointer and the tag being ORed together, as well as a mark bit being unconditionally set. So this mark bit setting is referred to as black allocation. So let's say that a concurrent garbage collection is taking place, and it's marking objects in the heap. If objects are being allocated simultaneously, they must be marked or added to a work list, because otherwise the GC may not find them, and so those objects have to start marked, and we call that black allocation. And in this case, however, entries in the C++ heap pointer table were unconditionally black allocated. And as we'll see, this was a security critical issue. So let's walk through an example in the general case. We've seen how when DOM API objects are created in JavaScript, they exist in the V8 heap as a script wrappable object. And this is what we can touch as an attacker with a read-write primitive within the V8 heap sandbox. As discussed earlier, these objects use the C++ heap pointer table to reference their corresponding objects allocated on the Blink heap. In this configuration, if we imagine creating some DOM object from JavaScript, deleting all the references to it, and then triggering garbage collection, both the JavaScript wrapper and the Blink heap allocation will not be marked. However, because the C++ heap pointer table entry is marked unconditionally, it will be marked. So we've labeled the wrapper, the table entry, and the Blink heap object with some type A. As an attacker, what we want to do is cause a situation where the table entry and the Blink heap object have different types, because this is the trusted relationship. The relationship between the embedder field and the C++ heap pointer table is not trusted, and that's what we can alter arbitrarily as an attacker. So after a collection occurs, we can end up in a situation like this. Both the V8 heap wrapper and the Blink heap object are freed, but the table entry is still allocated and still points to the same position in memory that it pointed to previously. Now, if we allocate an object of type B followed by an object of type A, we can end up in a situation whereby the original table entry with tag A points to the Blink heap object of type B. And then as an attacker with a read and write primitive inside the heap sandbox, we're able to overwrite the key in the script wrappable to point to the type A wrapper to the original type A entry, which gives us a situation like this. So the final configuration means that we have a script wrappable of type A pointing to a C++ heap pointer table entry of type A, but then pointing to a Blink heap object of type B. And because the wrapper and the table entry both have the same type, this doesn't violate the tagging scheme and allows us to leverage a type confusion. This is what a proof of concept exploit demonstrating the issue looks like. So first we create a DOMRECT, and we read its embedder field index and save it. Then we delete it. We delete the reference to the object, and deleting it in this way means that a subsequent garbage collection round will free it. Then we trigger a major garbage collection, which frees the object, and then reclaim the memory with the DOM matrix allocation. Then we create a DOMRECT to reference the dangling table entry. Now, writing the data fields to the data fields of the DOMRECT will corrupt the body of the DOM matrix. Cool. So in summary, garbage collection makes for a very interesting research focus. It's under heavy active development with, as we've seen, entirely new collectors being added and supported. In the end, subtle implementation details can lead to critical bugs, and so it generally offers a very rich attack surface. Additionally, understanding how V8 moves objects around is always really handy when you're working on exploits. And now, we have a demo.
All right, so let's go open a new tab. Let's go to this very nice website. Oh, first. So looking at the logs, there's not too much to see, but we see just the first stage. We end up with an array with a corrupted length. Then with that, we get arbitrary read-write over the JS heap. And then we escape the heap sandbox using the embedder field swapping that John just talked about. OK, back to this. Right.
Any questions? Hopefully this has left you less confused than this particular minor MS issue commenter that we happened upon while we were doing this research. But yeah, that's it. Thank you very much.